Hello and welcome to this webinar, EMWorks webinar series. Today's topic is about generator, how you can use EMWorks Solutions, EMS and EMWorks2D to design your generator. Okay. So the agenda is as follows. We're going to talk about design challenges for creating or generating or building a generator, and what type of EMWorks solution would be proposed to you. Then we will show you an example of a generator, synchronous generator using EMWorks2D, and then that is radial flux, and then we will do a more complicated problem, which is an axial flux, which is fully 3D using EMS 3D. After that, we're going to give you a live demonstration of the software itself. Okay, so synchronous generators are everywhere nowadays. Transportation and power generation. In an airplane, you have so many generators, you know, whether at the loads or at the auxiliary power units. So there are tens of generators in one single airplane, like this. In this case, 787, Boeing 787 electrical systems. Ship propulsion system, they also have so many generators, and so generators are everywhere, so you better know how to design and optimize them. Okay, all right, so these are the design challenges. So, how to predict the output voltage of your generator using different magnets and or rotor currents. Okay, because those they depend a lot on this parameter. How to calculate the output voltage of the generator versus operating speed. You know that the operating speed affects the voltage and the back EMF. Short circuit is very important because you have to properly design your generator in case of a short circuit, because the current will be much higher. So we have to design the proper fuses for your generator in case there is a short circuit. Then how to evaluate the generator and the different modes. You can have R, RL, RLC, and so on and so forth. Losses are very important for generators. So how you compute winding loss, eddy loss, core loss, so on and so forth. And we know losses cause heat. So how to calculate the heat caused by various EM losses. And we know that heat causes deformation. Then how to estimate the deformation of the generator under thermal stress. And lastly, how to investigate the breakdown level of insulating parts. What we propose to you is to use EMWorks solutions. EMWorks solutions are fully integrated in the most popular CAD, namely Solidworks and Autodesk Inventor. You can do both 2D and 3D, meaning radial and axial flux. Okay, you can do static, harmonic, time varying. You can do electric field analysis, parametric, multi-configurations in SolidWorks, or you can do parametric right in the EMS and EMS2D solution. Coupling to motion is very important, because you know that generator moves, whether it's a linear or rotational, is going to create a current. So motion is very important. So we have we claim that we have the best motion solution, especially for EMS, because it couples to SolidWorks motion. And multiphysics capability, they take care of the heat as well as linear static. Also, circuit simulator, because your generator is connected to a circuit. It cannot function in the air like that. You have to connect it. You have to feed it with a current and voltage. Linear and nonlinear element both are supported. Okay. These are basically the solution that we propose to you. We have various solutions. The EMWorks2D is a 2D solution, both plane and axisymmetric. You can do electrical and magnetic field simulation with coupling to motion. You can do parametric study, circuit simulation, and this is primarily for radial flux, because radial flux generator or motors, it is practically 2D because it is invariant along the longitudinal direction. EMS is fully 3D, so you can do axial flux motors and generators, and again it has similar capabilities, 2D, and coupled to motion, parametric study, circuit simulation, thermal and structural coupling are all in EMS. We have also a motor wizard. It's a template-based motor CAD design and simulation software. It has semi-analytical and finite element solution, and is not for all models. Okay, for certain models we have motor wizard solution, which is of course much faster than truly a finite element solution. Can do motor and generator mode, both of them. You can do DQ and X cognitive torque, no load and on load analysis, and we have a performance calculator. Okay. These are tools that we propose to you to tackle your generator design issues. All right, let's just start with an example. So we have a model. We're going to start with the radial flux. So it's 2D generator. It has 30 poles, 30 slots to pole. These are the number of poles. The mechanical speed, 12,000 RPM. The rated current, rated voltage, excitation current, and rated power. So this is the model for this radial flux generator. Okay. Of course, as we said earlier, we're going to show you a live demo of the software itself, but now we're just going to give you a taste of the results that you'll expect in the live demonstration. So, of course, flux, magnetic flux results, okay, in this case is a no load analysis, are extremely important, because that's going to tell you distribution and above all the saturation levels. And in this case red is really close to saturation, so you don't want to saturate your generator because your back EMF is going to drop. Okay, so this is you can do a contour plot, vector plot, fringe plot, so on and so forth. You can also do the air gap flux density. This is a plot in the air gap. And so EMWorks helps in optimizing the generator, reducing the saturation level in this steel, and increasing the air gap flux. And we know the air gap flux, the higher the air gap flux, the bigger the back EMF and the output of your generator. Okay, this also if you want to do no load analysis, we get back EMF results in this case, or short circuit analysis. We have coupling to circuit. Okay, so we have a circuit simulator editor. Okay, this is the rotor and the winding, and this is the stator winding. Okay, you can get the back EMF for because it's a three-phase stator. Okay, so this is back EMF versus time. Right. You can also have the back EMF results versus different parameters. For instance, okay, you can have the back EMF versus number of turns in the rotor winding, versus excitation current, versus speed, so on and so forth. So back EMF increases with speed, and the rotor magnetomotive force MMF. Okay, And this is of course known to you, but just wanted to emphasize that the EMS2D can indeed do that. Okay, you can do an on-load study using different loadings. So you can do just an R loading, like in this case, an RL loading, an RLC loading, and you're going to see the effect of different loading on the current. Okay, they don't have much effect on the back EMF, but they definitely affect the current in various coils or various phases. Okay, and these results are again the output of EMWorks2D. So you have the current, you have the voltages for three-phase output. So you have current and voltage. Okay, waveform versus time for the three loads. Okay. All right. So these are some again taste of the results that are generated by EMWorks2D for radial flux generator. Now let's move to the more complicated problem, is the axial flux PM generator. Okay, as you know, the radial flux, the flux is rotates like this, where you have bearings, iron core, magnets, coil, bearing, and this is the direction of magnetic flux. And the axial flux, okay, it rotates. The magnetic flux, this is the direction of the magnetic flux. Now, mathematically speaking, this can be simplified because of the radial flux. Okay, you can simplify it to an axisymmetric 2D problem, whereas the axial flux is a fully 3D. You cannot simplify it. And you know, the axial flux generators are relatively new, maybe in the last 20 years, but radial flux generator and motor has been there more than 100 years. The radial flux generator has a certain advantage. It gives you a shorter length and compact structure, less weight, suitable for e-mobility application, and reduces losses and higher efficiency. That's the reason you see more and more nowadays, especially in electric vehicles, axial flux motors and generators. Right. Using EMS, this is a taste of the results. Okay. So this is the magnetic flux density. This is a fully 3D. Okay. The air gap flux. Okay. And air gap flux from one rotor pole to the second rotor pole, and this one is between along an arc between rotor cores. Okay. To maximize the output and the efficiency of the machine, the air gap flux should be maintained at a higher level and have a uniform distribution. This is why it is very important to use simulation like EMS. Okay. In axial flux machine, designers study different holdback configuration, optimize the machine air gap flux, and that's again the big advantage of the axial flux generator and motors. Okay. These are some results again of the EMS. As you can see, as it rotates, it's showing the induced voltage. Okay. Okay, these are some results obtaining EMS. Okay, let's look at the first one. This one, the voltage, induced voltage, back EMF, versus grade for ferrite magnets. Okay, and then this for neodymium magnets, neodymium magnets, and this one for samarium magnets. Okay, as you can see, the output voltage is higher. Okay, for neodymium magnets. Okay, but that comes at a price. The neodymium magnets provide the highest output power, but they're costly and heavy because of their higher mass density. That's why we can see that they have same ratio of price to performance compared to magnets made of ferrite. Axial flux machine has the possibility to operate using multiple stage of rotor and stator cores. Okay, so you see here, price to performance, the ferrite and neodymium magnet actually are not very far off. So even though the neodymium magnets give you higher output, but it's not necessarily your best choice because of the weight and the price. Okay, so these are very relevant design conclusions arrived at using EMS. Okay, so to improve the efficiency and the power, designer add more cores while keep using a compact structure. In this case, ferrite magnets can be used since they are lighter and cheaper. So we can have a machine with more poles and less weight, but deliver the same or even higher power compared to neodymium magnets. So choosing the appropriate magnet should also depend on other criteria like temperature, operating temperature, and the corrosion resistance. So it's not always given that the neodymium magnets are the best, not necessarily. Okay, so this is important conclusion we reached using the EMS software. Okay, these are some more results using EMS. This is a multi-stage axial flux generator, as you can see here, sandwiches. Okay, it's like a McDonald's Big Mac. Okay, and multi-layer PCB axial flux machine. So of course the voltage increases, the output voltage as with the speed. These are some. This is the short circuit using EMS. This is the current, and this is the operating current at short circuit. And of course, the short circuit currents are 10 times higher than look at short circuit. Look, this is the operating conditions. This is the around maximum around 6, and this is more than 60. So mind you that you have to properly design, okay, your short circuit response, okay, to protect your generator, your valuable investment, okay, by choosing a protective system using the right fuses. So this type of analysis, of course, you can go to the lab and experiment with this, and of course, waste a lot of money and time. You can actually do the simulation right in EMS. You test your short circuit, and you know, okay, why it's important to do a short circuit run to know your current in case of a short circuit. So you're going to have the proper fusing and proper protection of your valuable investment. EMS is also coupled to circuit. Okay, so this is the equivalent circuit of the generator. Winding losses as a function of time. You can see the core losses as a function of time too. So under the load operation, because this is a load operation, okay, more electromagnetic losses are generated. Unfortunately, that's what's the case. This can affect the efficiency of the machine and lead to additional cost of maintenance. Hence, those quantities should be studied carefully during the design of any electrical machine, and especially a generator and motor. Okay, wind and core loss results are computed by the EMS software. Offer the capability to use these losses to calculate the temperature of the machine. So not only EMS gives you the losses, both core losses and winding losses, it actually from the losses it computes the thermal loss, heat load, and feeds them into the thermal program to actually give you the actual temperature distribution. Okay, and so these are eddy losses, for instance, as a function of time. This is the current density, namely the current density, eddy current density, okay, versus time, eddy current losses in particular, okay. This is the actual temperature. So EMS takes the losses, automatically feeds them into our integrated thermal solver, and it actually gives you the actual temperature everywhere in the model. Okay. So variation of temperature versus time. This is temperature on the stator parts. And not only that, from the temperature, okay, you're going to generate heat load, right? And the heat load, heat losses, or thermal stress is going to cause deformation. And that is also done automatically. Take the thermal, the thermal stress, and we actually compute the deformation for you, okay, right in same integrated environment. Okay, this is just, of course, this is exaggerated, but this is the mechanical deformation in the rotor. Okay. All right. So these are some of the results, okay, of EMS 2D and EMS. Okay. And now we'll go straight to live demo of the software. Okay, so now this is EMWorks 2D. Okay, it is an add-in to Solidworks. So just in the add-in, you just click the additional software is EMWorks 2D and EMS. All right. Okay, now let's go to our model. This is the model of our generator. Okay, so let's look. And again, because this is integrated inside Solidworks, so really creating the geometry is really as easy as a pie. It's extremely easy. And because Solidworks is parametric, you can change, you can do all kind of geometrical changes at no time. And you don't need to export or import after that, because you are right inside Solidworks. So click in EMS. This is EMS, is 3D, and this one the EMS 2D or EMWorks 2D. Okay, and we'll show you how to do a study. So first study, I'm going to go to the properties, and in this study you say compute energy, compute circuit parameter. Okay, and this is the because transient, so time, coupling analysis. So we say, of course, rotation, motion, and coupled to circuit, a constant velocity, and 72,000 degrees per second. Okay, and this is the coupling to motion. That's how you can couple to motion. Okay, advanced properties. Yeah. So in these cases, we are using second order. Okay, higher precision. All right. That's all you need to do. Applying material. Load, boundary conditions, and all of that is very straightforward. We have many videos in our YouTube channel. You can refer to them, so let's not waste time doing that. We're going to go straight to the winding. So this is the this is the plus, this is the minus, the rotor winding, and the phasor has three phases, A, B, C, and this, of course, plus or minus, plus or minus, plus or minus, plus or minus. And again, you can refer to other videos that it gives you a detailed explanation how you set up your problem. Let's just want to before showing the results, I want to show you the schematic. And this schematic is integrated right in EMS. So it's a circuit simulator. In this case, this is the presentation of the rotor, and this is the stator, and you have three phases, and in this case we have an R loading. Okay, so this resistive loading. Okay, so first set of results to the results table. Okay, for each position, okay, you have the energy the angular position, the speed, the resistance, winding loss, flux linkage, okay, in current, induced voltage. Let's just do current, for instance. And if I want to look at the current in three phases as a function of time, okay, and there you go. So I have this for phase, three phases, okay, and A, B, C, and we have the how the current changes as a function of time. Any other quantity is plottable as a function of time or position for, okay. So you can of course export the results, you can print them, and so on and so forth. So if I wanted to for instance see something else, if I wanted to see the induced voltage instead, then I can, for my phases, I say add and plot, and there you go. And this is my induced voltages. All right. That's what we call circuit and motional quantities, or mechanical quantity, because it has a torque as well. You can also look at the magnetic flux density. Okay, in this case, you can do contour plot. All right, so this is my contour plot of my magnetic flux density. I can animate it. It's going to take a minute for the animation because I have about 41 time steps. So it's going to take just a minute. It's coming. Okay. So there you go. Now it rotates. As it rotates, you can see how the magnetic flux density changes as a function of position and a function of time. You can do fringe plot. Okay. You can do vector plot. Okay. And all of them, in all cases, you can animate. Okay. Another type of plot is the 2D line plot. If I want to see what's happening, for instance, the value, say, if you go to time step number 2, and I want to go from this point to this point in this segment, okay, and I want to plot, okay, and this is the plot of the magnetic flux density as a function of distance between the segments along the segment. Okay, of course you can see the text format. You can of course export, print, and so on and so forth. Okay, same thing is for the magnetic field. You can plot your magnetic field, and it's 0 because it is first time step. If you change your time step, of course it's going to change. Okay, okay, and of course you can animate. If you want to animate your magnetic field, okay, definitely it's going to animate for you. Okay, it's coming, it's coming. All right, there you go. You can plot, if you wish. You can apply the you can plot the applied current, okay, and losses, magnetic current density. If you want to see the eddy currents, okay, and these are basically table field plot. You can also plot your current. Okay, in this case. Okay, in the three phases A, B, C, okay, the current, okay, as a function of time or positions, okay, flux linkage, induced voltage, okay, okay. So this is the R load, just resistive load. We can do, in this case, the problem is exactly the same, except with a different load. In this case, we have an RL loading, okay? And you can see exactly same results, of course, different, based on the load can have, it has an effect, you can definitely look at the current again, and so on and so forth. So and then you can also do a different loading. The setup is the same, except the circuit is different. Like in this case, okay, so in this case we have an RC loading. Okay, plots are the same. Everything showed you in the first study with just R loading is exactly the same. Okay, the last study is slightly different. Why slightly different? Because actually it has no load. Actually, this is what we call short circuit analysis. Okay, as you see, there is no loading at all for the phasor, the stator phase winding. Okay, and you can again do all the all same type plot and flux linkage, induced watt, and so on and so forth. Okay, now let's now compare. If I want to compare now my results, okay, go compare results, and I'm going to go to transient magnetic. Okay, and now one thing is the induced voltage or back EMF. Okay, so if I look at, say, I'm just going to take one phasor A. Okay, and now I'm going to compare. All right, so yeah, it's the same. So what is the conclusion? Whether you have loading, R loading, RL or RC, or no loading at all, like in this case, back EMF at the stator phases is the same. It's really very little variation, as you can see. Okay, this is one conclusion you can reach. Okay, now let's look now at the current. This is my current. Okay, and I'm going to look at this phasor again. Add. Aha! Now we see the differences. So the no load, it's zero current, right? So that is what it is. Okay. Now we can see the shifting that takes place. Okay, so the blue is just R loading. Okay, if we add an inductance, we're shifting to the right. If you add a capacitance, we're shifting to the left. So in this, this is very important to see the effect of the loading on your current. Okay, you can also compare any other quantities for different studies. So this all the results table, you can see them here. Actually, if I want to say do the torque, okay, and I can see. All right, so I can see the torque. Okay, the torque for the no load analysis, you know, it is basically, it oscillates around zero. See, really on the average it is almost zero torque. Okay, whereas I have a higher torque with just the R loading. Then it comes the RC and RL loading. So you can see the effect. You can smooth if you want these plots. Okay, you change the individual plot and smooth if you want to see smooth results. And this is for all type of plots. You can do this. Okay. Now last one. Okay. Still one of them not smooth. What is this one? This one here. Okay. So this torque, the effect of the loading or no loading on the torque. the output torque of your generator is also equally important. So in the compare results, you can compare results for any number of studies. And there's another neat feature is I run all studies. So suppose I generated 10 studies, loading, no loading, different loading, different material, different, and I can actually submit all of them at once before I go home in the evening, say, run all studies. And when I come in the morning, I shall find all my results, then I can do compare results and see the effect of varying different parameters. So this is what we call virtual prototyping. So this is as far as the EMWorks2D for radial flux generator. Okay. Now I'm gonna close this one. Okay, and actually open the actual. I'm not gonna save. So I'm going to actually open the 3D generator. And as I mentioned earlier, it is fully integrated in Solidworks. So no importing, no exporting, no mess. Okay. So now I'm going to click on EMS, and the idea is the same. Okay, it takes a minute because it's large, like the 2D. So this is an axial flux. So the axial flux, because it is 3D, it has more parts, it's heavier. Okay, so if you have a radial flux, you always recommend for you to use our 2D. Okay, so let's just see the properties. Okay, the coupling in particular. In this case, I said thermal coupling, circuit coupling, motion coupling, and this is where it's different from the 2D. In the motion coupling, I'm coupling to Solidworks motion, so I can do the exotic motion setting, exotic motion with 6 degrees of freedom because I'm using Solidworks motion. So I decide to which motion study I couple. Okay, and that's all. That's it. That's all I need to couple my EMS study to Solidworks. Okay, so winding are winding. Okay, so I have 3 windings. Okay, and of course in this case I have my permanent magnet. These are different materials. Okay. Okay, notice something here, that I have electromagnetic input and thermal input. Okay, why? Because it's coupled to thermal. So in my electromagnetic input, I'm going to specify the boundary condition and forces, coils, and the thermal input. Actually, in this case, it's a full-fledged thermal solver. I can specify temperature, convection, heat, flux, but in this particular case, I just have convection. Yeah. So it's air convected, air cooled. Okay, and that all it takes for me to couple to thermal. And of course, your material better have the thermal property and electromagnetic properties. Okay. All right. Now my schematic. This is my schematic for the 3D. Okay. So we have just the three coils and resistive loading. Okay. Now let me just jump straight to the results. Exactly like same architecture like 2D. I have a rich set of results. Okay, so these are the motion results. Okay, so if I want to, for instance, plot, okay, my displacement, okay, angular displacement, it goes from 0 to 60 degrees. It's a function of time. Okay, and all of these quantities, as you can see, torque, current, inductance, flux linkage, induced voltage, winding loss, core loss, resistance, energy, so on and so forth. Okay, so in this case, let me just show you how to plot not the force. Actually, I want the torque. Okay, so this is my torque. Okay, and I can smooth it. Okay, as a function of time. And again, I can see it in text format, export it, print it, so on and so forth. So any of these quantities are plottable as a function of time. And again, I can export my results or print it. These are the tabulated or table results. Similar to the 2D, I have my field plot, right? So this is my fringe plot. I can do animate, okay? And let's see, I have 31 points, and 1, 2, 3, and go. Now it is rotating, okay? See, the rotors are rotating. I have 2 rotors in this particular case, and the stator in the middle. So it's showing me, and it's really in some places really reaching almost saturation. Okay, I can do a section plot. I can animate this time versus section. So what it's going to do is going to take different slices, okay, and it's going to move. Can do vector plot, or can do, let me see, do vector plot, no clipping, okay, and definitely if I want to activate, animate my vector plot, I can do that too. Now you may ask, why doing a different problem when doing EMS? Why not using same problem? Well, because in regular flux you don't need 3D. 2D is good. This is an entirely different problem because it is an axial flux generator. So, of course, as I showed in 2D, you can do H, magnetic field, current density, of course. If you animate, you're going to see, because it's 0, it's there you go, as it rotates the current in different phasor current. Current density. Similarly, I can plot the electromagnetic parameters, and in this case, core loss as a function of time. Okay, I can plot linear plot of any of these quantities. Is a force, current, inductance, losses, so on and so forth, core loss or eddy loss if I want. Okay, this is my eddy loss. Okay, so any of the table quantities are plottable as a function of time and position. I can plot. There you go. Okay, my temperature, if I want to see cross section, different parts. Okay, I can, for instance, if I want to see the temperature only in one given part, if it's in, okay, while this one is actually constant in the rotor, but I can see maybe the temperature right here is also okay, constant. So where is my temperature then? Varies. Okay, yeah. So okay, so this is it, the temperature. Let me see the entire model. Okay, so why is it then when I want to do edit field, and if I show temperature here, okay, so that's the temperature right now, isolated just in the rotor. So that's how my temperature varies. Okay, say okay. Right, so I can do, of course, temperature gradient, heat flux, so on and so forth. Okay, so this is the 3D for axial flux generators and motors. Last, I can generate a report, so I don't need to take notes. I can just customize my report. Say my name here, company, today's date, I can generate an HTML file. And this is a nice formatted HTML file that has everything about the study: the input, the output, the result, the dates, the material, force and torque, so on and so forth. So you can share it with other people on the internet, or you can generate a PDF file. Okay, and again, same thing. Have run all studies. Well, I have only one study here, but I can. Let me see how long it's going to take. Let me just copy this study, copy my study. Okay, now I'm copying everything, so I don't need to redo everything. So I have a brand new study now. It's a copy of this study. I can go ahead and change whatever I want in this study, and then I run all studies before I go home in the evening if I want to compare results between studies. So it's the same interface, same look and feel as the 2D. Okay, so to conclude, EMS, EMWorks2D, and EMS. So EMWorks2D is for axisymmetric and 2D, so radial, flux, motor, and generators. It gives you everything that you need about your generator. And then the sister program, the EMS, this is EMS, EMS2D or EMWorks2D, okay, is a fully three-dimensional that allows you to study. Of course, if you want to do a radial flux with 3D, you could, but we don't recommend because it's just a waste. Okay, but this is for your axial flux, motor, and generators. We truly recommend for you the EMS. So together with the EMS and EMWorks2D and EMS, you can solve all kinds of generators. Okay, and you can parameterize, you can design, you can do everything. Okay, with this software. And again, because they are integrated in CAD, that makes your life very easy. With that, I would like to thank you all for your time, and time for questions now. If you have any questions, please type it on the right hand side of the chat region, and we'll be happy to answer all of your questions. Thank you.